Our foundational map of the cosmos just shattered as new telescope data reveals a reality that defies our best math. For nearly a century, the Standard Model of Cosmology has acted as our master blueprint for the universe. It reliably predicts how matter clumped together and how galaxies drifted apart over billions of years. At the center of that model sits the Hubble Constant. It is the accepted speed limit for cosmic expansion, the single calculation that tells us how fast space is stretching right now. If that speed limit is wrong, our entire understanding of physics fails. The mathematical laws governing everything from massive galaxy clusters down to individual atoms would be based on a flawed premise. Physicists calculate this rate by looking at the cosmic microwave background, the ancient radiation left over from the Big Bang. This early universe data lets them project what the expansion speed should be today. This chart shows the result of that projection. It places the expansion rate at approximately 67 kilometers per second per megaparsec. But we can also measure the late universe directly. Astronomers track nearby supernovae and stars to calculate the expansion rate in our immediate cosmic neighborhood. Local observations consistently land at 73. This massive gap represents an irreconcilable conflict in our data, leaving a 6-kilometer discrepancy the Standard Model cannot bridge. Scientists spent years dismissing this mismatch. They assumed the Hubble Space Telescope had blurry vision, or that cosmic dust was obscuring the light from distant stars and skewing the local results. The James Webb Space Telescope was built to end that debate. Its infrared sensors pierce through cosmic dust to view Cepheid variables, pulsating stars that act as highly accurate cosmic mile markers with absolute clarity. Webb's mission was to audit Hubble's math. Astronomers expected the new, clearer data to reveal the measurement errors that would finally bring the local results down into alignment with the early universe. This graph shows how the two telescopes compared. Instead of a correction, we saw an undeniable overlap. Webb's data confirmed that the original measurements were correct. A team led by Nobel laureate Adam Riess verified these findings across thousands of stars. The equipment wasn't the problem. The universe is objectively expanding faster than our laws of physics currently permit. This spiral galaxy represents a multi-billion-year evolution that is currently challenging the very limits of our observational technology and theoretical physics. Webb's confirmation eliminated the equipment excuse. The physics community now faces a systemic crisis that cannot be solved by simply cleaning a lens. The mystery deepened when a team at the University of Chicago, led by Wendy Freedman, conducted their own independent audit using Webb's data. The Chicago team used a different methodology, cross-checking distances using 3 different types of stars, Cepheids, red giants, and carbon stars, within the same galaxies to ensure accuracy. Their calculation came back at 70 kilometers per second. This intermediate result matches the slow expansion predicted by the early universe data, directly contradicting the Riess team's higher speed. These conflicting findings suggest a fracture in the scientific consensus. It implies that certain stellar markers might possess unknown physical properties that are skewing our current readings. As the observational data grows more confusing, theoretical physicists are attempting to force the numbers to align by rewriting the foundational math of the Big Bang. This sine wave represents the primordial power spectrum, the infant universe's matter distribution. Theoreticians manipulated this spectrum to force the expansion rates to merge, but the math pushed back. As the spectrum stretches, the total matter density, omega m, drops to a level contradicting every other observation. The Standard Model is a tightly intertwined ecosystem. Patching a single isolated leak in the expansion rate causes the structural integrity of the entire model to collapse. Cosmology now faces a choice: uncover a hidden flaw in every measurement we've ever made, or accept a missing chapter in our physics. The leading candidate for that missing chapter is early dark energy. This hypothetical phantom energy would have acted as a temporary accelerator shortly after the Big Bang, giving the cosmos an extra outward kick before vanishing. This would bridge the gap between our early and late universe data. This friction between our measurements provides the clearest evidence in a generation that our cosmic blueprints are ready for an upgrade. By following these conflicting threads back to the Big Bang, we are finally mapping the invisible forces that truly govern our reality. These contradicting data points have given us the raw materials to construct a more accurate and comprehensive model of the universe.